Okay, wonderful. So, so what were we doing in the last class? So you're looking at logical foundations of Prolog, and we looked at this way of computing the answer to the query ancestor Rickard Rob, which used SLD resolution in order to find the query, right? So in order to find the whether the query is part of the least headbrand model of the program. And we sort of went through it by hand. And the high-level takeaway from that particular exercise is that in Prolog, unlike other languages, when a Prolog program computes, it is actually doing logical reduction, right? So when you ask a query, what it's trying to do is to answer a question about satisfiability, right? And it's a really interesting model of computation that is different from um, how all of the other models of computations that you've possibly seen so far, right? And this sort of computation is common to um, all the logic programming languages. But in our example, we picked a particular form of logical reduction through SLD resolution. In particular, in SLD resolution, what you do is you take the program in the order in which it is written, and we search for matching unifying clauses in the order in which they appear in the program, right? And whenever we found a matching clause, we did a depth first search for proof, right? Until we hit the result. And then finally, what we did is when given a conjunction of goals, essentially we saw a conjunction when we had an ancestor query which involved a parent and an ancestor, recursive call to ancestor. In depth first order explored G1 and then explored G2, right? So SWI Prolog, which is what we are using in this course, is one Prolog implementation, and it picks the performs the reduction using this algorithm, right? But other Prolog implementations may choose to adopt different strategies. Say, instead of depth first search, they can use breadth first search. Or when you're given multiple goals, it may choose the last one instead of the first one and so on. So each of these leads to different results being observed, actually. In particular, because we have certain features in Prolog which don't really nicely fit into this logical framework, but are still useful. So at those places, you'll see the difference in the order in which you resolve the computation matter. So the high-level takeaway is computation is deduction, right? So there's a question. Let me try to answer that. So Srisha asks, does Prolog remember memorize facts along the way? So it does remember where it is in the search tree, right? So it's searching, so it knows where it is searching through, and it applies unification, right? So there is no need for it doesn't do explicit memorization. All it does is certain unification. So if you have certain variables which you found an answer to, and that's like a constraint, right? And if you satisfy that constraint along one path, it remembers that path in that branch. But sometimes it may so happen that you've gone down the wrong path and you have to come back. At that point, um, you need to sort of erase your unifications that you've done. This is known as backtracking. We will see all of this later. But Prolog doesn't do explicit memorization of facts along the way. It simply does a search through the program, right? And it knows where it is in the search tree. They're essentially building a huge tree of search, and it knows where it is. We will look at all of this when we actually work through certain examples by hand. We'll go through it in the coming lectures. Okay, so the thing that we did in the last lecture, towards the end of the last lecture, is we took this program and we sort of traced through this program by hand, right? And SWI Prolog has a tracing facility built in. This is not exposed in the Jupyter notebooks, but it's still useful for debugging programs. So I'm going to show you how to do this tracing in SWI Prolog. So let me. So if you let me exit from full screen first. Oops. Okay. Are you able to see this? I'll make it bigger. Can someone confirm whether the font size is okay?
Yes, sir, we can see.
Okay, wonderful. So when you start your Docker container, right? The first thing we do is start the Jupyter notebook. But the other thing that you can do is actually run any commands in the shell. So one of the things that have been installed in the Docker container already is the Prolog interpreter. So if you say, I think I already have a Docker container running here. But if you just start the Docker container and then type swipl, you'll see something like this. So this is the Prolog interpreter that's running. And what we are going to do is to try to run this program by hand. So when you run the Prolog interpreter, right? So it prints out something and then immediately stops at question mark minus. So essentially, it is waiting for your query to be answered. Initially, when it loads up, it doesn't have any facts or rules loaded up. So let's first input the program. So one way of inputting the program is actually typing out the program directly in the interpreter. You can also load files. We will look at it a little bit later. But the way to input the program by hand is you type this command user dot, and then if you press enter, you enter this mode where you can type the program, right? And what I'm going to do is to copy all of the facts and rules, right? I'm going to paste this here. Yeah, everything is pasted. And then the last thing that you do is if you press Control plus D, I press Control D, and Prolog says that this program has been compiled with 9 clauses, and it prints true. But all it says is okay, it's loaded up the program. Now we can ask the query, right? So this is the query ancestor record Rob. If you ask the query, it's going to come back with true, right? We know that Rickard is the ancestor of Rob. So what we want to do is to trace through the program, right? Let's trace through the program. So the way tracing is enabled is there is a query called trace. It's like a meta query. Prolog knows about this query. So trace is essentially a query, but it has some side effect. In particular, it turns the tracing facility on, right? So this says trace is on here. So now let's do the same query as earlier. Okay, so if you do ancestor record Rob, Srisha, you're unmuted. Can you mute your mic? Thanks. So now I'm tracing. Okay, so what is happening now is I'm actually going through the program step by step. This is replay. That's okay, Srisha. Totally fine. So what is happening now is we are going to trace through the program step by step. So the first thing that we ask is this query, right? Ancestor record Rob. Prolog says that I'm going to call ancestor record Rob. And what call says is I'm going to try to satisfy this goal, right? And it stops there. What is going to happen when you, let me make this bigger. Oops. So what is going to happen when you ask ancestor record Rob is it's going to search through all of this. It is going to find the first matching, first unifying rule where it can satisfy record Rob. That would be this one. Oops. That would be this one. And it's going to try to change the goal to parent record Rob, right? So if you press enter, you can see that the call now is now at parent record Rob. It is now here. And now, if you go through it again, parent is going to lead to father XY, which is father record Rob. If you press enter again, now this is going to be father record Rob. And Prolog is going to search through all the facts in the order in which they are presented and observe that there is no father Rickard Rob fact in our program. So what Prolog is going to do is go all the way to the end and then fail, right? So if you press enter, so it says that, oh, this particular call has failed because I couldn't prove this particular fact, right? I couldn't find any unifying facts or rules that can satisfy this. So I'm going to fail. So when you fail father, you also fail this parent rule, which was the recursive rule. You also fail the ancestor rule. But for the ancestor rule, we have another option, right? We only tried the first option. We're going to try the second option. So which is why Prolog says redo, right? It's redoing that particular goal, and it's going to take a different path now. It's going to take the second path, right? And the second path has two sub-goals, parent and ancestor. In SLD resolution, which is what Prolog does, it is going to pick the first one, right? So if you, but observe that there is a Z here, right? There is no Z on the left-hand side, but there is a Z here. That's an existential variable, right? So we don't know what the result for that Z is. There is going to be some Z. What Prolog does is it will just rename that Z to some arbitrary variable so that it can keep on going and find a unifying, satisfying thing. So we'll see how it works. So if you call this, observe that now there is a parent record underscore 9534, which corresponds to the Z. All Prolog does is it renames every existential variable so that it creates fresh variables so that there is no conflict in those fresh variables, right? This is something that we've done earlier, if you remember, when we did substitution. The idea is quite similar. So it's going to continue searching for this, right? Parent goes to, what happens in the next step? Parent goes to father, right? Parent goes to father. And father record this variable 9524 unifies with the first fact, right? There is a fact here which says father record Ned, and that unifies. So if you press enter, observe that we have this new thing called exit, which certainly says that, oh, I have, now I was trying to prove father record some variable. I found a matching fact, right? And that fact had Ned as the variable. So I'm going to unify 95 underscore 9524 with Ned, right? So that's why it prints father record Ned. And when it steps out, you also see that this step here that corresponds to 9. 9 is the nesting level. That also corresponds to, because we unify 9524 with Ned, this 9524 is also Ned. And if you step again, so we've unified that existential variable with Ned, right? And that's the same existential variable that appears on the second subgoal. So we know that the value of Z is Ned. Now let's try the ancestor. So there also we replace that underscore 9534 with Ned. And we know Y is Rob, right? So that's why we get Ned Rob. And this goes through parent, and that goes to father. And we see that there is a father Ned Rob fact. So that will exit. And now we are at ancestor. We return to our original question. We exited. So that our complete goal is proved now, right? So we've satisfied, we found we asked a query whether this is satisfiable. It is satisfiable. So let's, and we are done. So Prolog just says, okay, that's true. And it exists. So this is how you can do tracing within Prolog. So, so yeah, okay. So, and the last thing that I want to show is you have tracing on. You can turn off tracing by this query called no trace, which gets you into this debug mode. Debug mode does not print out the results, but disables certain optimizations, which we will also see later. But if you want to get back to how it was earlier, there is a query called no debug. You always need a dot at the end. Okay, so remember that you need a dot at the end. When you press no debug, you're back at where you started. Okay, the tracing is turned off. Yeah, okay, so that's how we trace programs in Prolog, and this perfectly matches the way we work through the example. Any questions on this so far? Yeah, okay, let's do that. Father record X. So let's first query this, right? So there are multiple solutions for this. Actually, no. Why not? Okay. There are multiple solutions for this. Let me say how this works. So when you type further record net, Prolog sort of stops here, right? The reason why Prolog stops here is it's saying, I found one result. I have other results. Do you want to continue? If you press enter, you're saying, I don't want to see any other results. You can press semicolon. Okay, I think semicolon is the right key. So if you press semicolon, it prints more and more results until it runs out of results, and then it comes back. So your question is, what happens if you trace? You can trace it. Um, let's try this. So, so we are asking for x, right? So we have an existential variable there. So this is going to be satisfied with the first option. And when you press enter, this is going to erase the fact that you went down one path, and it's going to try again, right? So this is what is happening. Do we have a redo for existential variable? I think this is what you're asking, I think, Naman. We've explored one path, we have satisfied, we forget the fact that we did unification, right? So this is known as backtracking. We'll come back to this later. This is sort of when you have multiple choices where you perform unification down one path, you also have to undo unification when you come back and try other paths. That's what is happening here. If you don't understand this, that's fine. If you develop an intuition for this, that is also fine. You look at it in detail as we go through the lecture. But this is what is going to happen, right? So it finds the second one, it stops saying, I found a satisfying X Brandon. If you press semicolon again, it goes through and reads us the thing and finds Liana and then prints and exits. Okay, I think I've answered both of your questions. So any other questions? No. How do I put it? No, it's not doing any memoization. So if you ask again, and it's not visible here, but it's actually running everything again. But you can imagine memoizing it, right? So of course, memoization is a useful optimization, and real implementations would um, can and would memorize the results, but I don't know whether SWI Prolog does. We will never. I don't think we will ever write a program that where you can actually measure time. Good question. I think it's an important optimization, but I don't think we are doing memorization here. Anyway, okay. So yeah, okay. So let me switch back to the lecture. Yeah, if you want to look at the commands, there's an image of this here, and you can find out what the commands are. And that concludes the logical foundations lecture. So let's move on to the next lecture. So what we're going to do in this lecture is we're going to try to show like a simple use case for Prolog. So this is solving. Oops. This is solving a logic puzzle, and and it's a fun problem. I think we'll go through this, and I think you will appreciate this puzzle. So some of you might have already seen this puzzle in one of your earlier classes. So have you heard of the zebra puzzle? Anyone? Yes, no? So we are going to look at solving the zebra puzzle using Prolog. So for queries with, Vishnu has a question. For queries with existential variable, does Prolog try to deduce for each constant? If so, what will happen if Hermann base is infinite? Really good question. So that's what gives us non-termination. So um, we will have examples where you will see that there are infinite number of answers for certain questions, and Prolog execution will be infinite. An example of this is give me all the last elements of a list or something, and then you replace both the list and the last element to be a variable, right? And of course, there are infinite number of questions, infinite number of lists, and infinite number of last elements that can satisfy this. So yeah, so it does go into that. If there are infinite number of results, it gives you infinite number of results. And we will look at ways of sort of saying, give me the first 10 results or something. Okay, coming back to the question that I asked, has anyone does anyone know the zebra puzzle at all? No. Okay, I thought you have covered this puzzle in one of the earlier classes. That's what I remember from the last year. Anyway, it's a very simple puzzle. Okay, so what we're going to do is to solve this puzzle. This is like a classic newspaper style puzzle. The puzzle itself is here, right? And there is this 15 facts. Okay, so it's describing a set of houses and a set of properties about people who live in each of the houses. And we are going to ask a question about who drinks water, who owns the zebra. The facts are there are 5 houses. There is an Englishman who lives in the red house. The Spaniard owns a dog. Coffee is drunk in the greenhouse. Ukrainian drinks tea. Greenhouse is immediately to the right of the ivory house. Old coal smoker owns snails. Cools are smoked in the yellow house, and so on. Like there are lots of facts like this. And these are essentially constraints, right? There are 5 houses, and each fact is a constraint that is sort of restricting the set of possibilities for what the houses can be. And these constraints are sufficient to figure out who drinks water and who owns a zebra, right? You can work it out on paper. I don't think this is a difficult problem, but it's nice example to sort of show Prolog's execution. Okay. So how do you take this puzzle and then convert it into a Prolog program, right? So this is one way of doing it. This is not the only way. Of course, you might think of other ways to do it, but let's look at how we've done it in this lecture. So we have the fact that there are 5 houses, right? And there are some facts about the people. I mean, each of the houses, right? What are the facts? There is a notion of a nationality of a person who lives in the house, right? Englishman, Spaniard, Ukrainian, and Norwegian, Japanese, right? And then each house has a color. Red is one. I think green is another one. Each house, there is a pet in each house. There is a dog in this house. I think there is a cat somewhere. Snails. I don't know why you would keep snails as a pet. Horse is kept here, right? And then there is a drink that is drunk in each of the houses, and there is a brand of cigarettes that is smoked in each of the houses, right? Old coal, cools, and so on. So those are the 5 properties, and we also have some spatial information about the house. So there is this constraint of right? Greenhouse is immediately to the right of the ivory house. Milk is drunk in the middle house. Norwegian lives in the first house. Cools are smoked in the house next to the house where horse is kept, and so on. So there are some properties, there are some spatial information, Let's try to put it all together in a Prolog program. Okay. So as I mentioned, each house has 5 characteristics: nationality, pet, a smoke, drink, and color. We know that these are all the 5 characteristics, right? So we can define a house as a function, right, which has these 5 properties. So house is a house is a compound term, right, with 5 properties, and we will represent a street, a row of houses, as a street with H1, H2, H3, H4, and H5. Okay. So that's our basic representation. So a few questions. What sort of a term is this house, nationality, pet, smoke, drink, color? Observe that I'm using capital letters here. These are variables. Okay. What sort of a term is this? Is it a number? Is it a compound term? Is it a variable or a constant? Yeah, compound term, right? So, okay. So, what sort of a term is this? You don't have a top function symbol, but you have a tuple, which is 5 things. Assuming that this is a well-formed Prolog term, right? What sort of a term can this be? Take it from me that this is a correct Prolog program. No, it's a compound term. So the reason why this is a compound term is that it's a tuple, right? In Prolog, tuples are compound terms without an explicit function symbol. So you can sort of think about tuples as tuple 0, tuple 1, and so on. I mean, I haven't told you this, but so this is the top function symbol is sort of like a tuple with 5 things, right? And those 5 things are the 5 variables. So this is a compound term. Okay, so that's the answer. Okay. Okay, the first thing that we are going to do is we are going to assert some facts, right? We are going to say Englishman lives in the red house and so on. And we want to say something like there exists a house in the street where the Englishman has a red house, right? There exists a house in the street where some ivory house has some snail or something. So the way we are going to capture that is define a predicate called exists that capture this fact, right? And there are 5 houses in the street, so we are going to have 5 facts. The way to read this fact is there exists a house A in the street of houses if what is the predicate? It has to be one of these 5, right? And we have 5 facts for each of these 5 positions. So we say A exists in the street if A is in the first position in the street. A exists in the street if A is the second position, third position, fourth, and fifth, and so on, right? So this is a easy way of saying that a house exists in the street, right? So we have 5 clauses added. So let me make this bigger. So we are asking whether H1 exists in the street. What is going to be the result of this query? It's only going to say true or false, right? It's a true or false. True. Yeah. And H2 is also true. What about the last one? H6 is in the street with H1 to H5, false. Yeah. So you don't declare anything unlike OCaml, right? Where you have to sort of say, oh, I'm going to use the street, I'm going to use exist and so on. You just define facts in Prolog. In that way, there are no types in Prolog, right? Everything is untyped except for the fact that you have compound terms, you have predicates, and you have constants and variables. That's all the things that you have. So you can happily start writing your program this way. Okay, so let's another quiz. So which of these queries return true? Um, so does the first one return true? Okay, so there's a question in the meantime. How to differentiate predicates and functions in Prolog? So good question. So predicates are the what appears as the top function symbol in a fact, right? So here, when I write exists and I have a dot at the end, so exists is a predicate that has arity 2, right? And and yeah, that has arity 2, and a predicate can also appear here. So you can have p1, some number of arguments, say a, b, c, right? And you can have p2, something, p3, something else, right? So P1, P2, and P3 are predicates, right? They appear either as a fact, I mean, they appear as a at the head of the rule, right? And they also appear in the body, right? As the top thing. So these are predicates, and functions are the things that can only appear here, right? Of course, we don't we don't sort of say um, if you define. So street is a function here, right? Street appears within a predicate, but I can also write street of 0, right? For whatever reason, I write street of 0. Prolog will accept this, right? Prolog will say, okay, this is fine. Um, this street is a function because it appears within the body of a predicate, right? This street is an actually a predicate. So Prolog doesn't distinguish that way. The thing that cannot happen is you cannot have predicates in the body of a predicate. Okay, so you can only have predicates at the top level. Does it sort of answer your question? I don't think I did a good job of explaining it, but okay. So you will sort of the things that appear within, right? Those are functions. Those are like function symbols, right? They are compound terms, really. So you can think of them as constructors essentially in OCaml. So they're a way of constructing some data, and these are actually facts and rules that we assert. So okay, so going back, right? So is the first one true? So there exists a dog in the street, right? True. Okay. So what about the second one? There exists a dog in the street. Um, yes. Okay. Good. So false is the answer because the arity is different, right? We define street. The the exists fact is applicable to a street with arity 5. There always have to be 5 arguments, right? If you define it with 4, that's not going to be unified with anything. This is simply unification at the end of the day. What about exists a dog? False. Okay. Good. So the last one is there exists a house English read in a street, and it's not very readable, but there are 5 houses here. And the last one is house English, comma, underscore. True, right? So because these two unify together at the end of the day. So English unifies with English, and red unifies with underscore. Underscore is a variable that unifies with it. Okay, good. Yeah, okay. So that's what I wanted to say. And we had this spatial predicates, a few spatial predicates, right? So it said what is the relationship between the houses in terms of where they are located. So we had this fact called fact number 6, which is greenhouse is immediately to the right of the ivory house. So we are going to define this predicate called right of. The way to read this is A is to the right of B, right, in the street if you have this configuration. So which is that B is the first one and A is the second one. So A is to the right of B. And there are other positions as well, right? So B is the first element, B is the second element, B is the third, B is the fourth. So there are four possible facts for this. And essentially the way you read it is A is to the right of B if the street has one of these configurations. Okay. And that's a predicate that we define. We also have the middle house and the first house. We say A is the middle house in the street if A appears in the middle. Right? And A is the first house in the street if A is the first house in this list. And we also have this next to predicate, right? Cools are smoked in the house next to the house where horse is kept. Norwegian lives next to the blue house. So we define next to in this way. So we use both a rule as well as four other facts. So we say that A is next to B in the street S if A is to the right of B in the street S. Because we had already defined right of, right? So we are saying A is next to B if A is to the right of B. We haven't defined left of earlier. So all we are doing here is we are also stating that A is next to B if A is to the left of B, right? A is next to B if A is to the left of B in these four positions. So that's defined. We've added 5 clauses. And okay, so now I think we've expressed all of the required structure to express the problem. So this was the original puzzle, right? And this is going to appear as a query that looks like this. I'll keep it smaller because I'm going to switch back and forth. So we say that there exists a house which, I mean, this is the Englishman, the nationality is British. A British person lives in the red house in the street, right? And this is the second of the facts, right? The first fact is encoded by the fact that there are 5 houses. So we fix the street to have arity 5. So Englishman lives in the red house is converted to this British person. The color is red. There is a house with British person in red color in the street. And similarly, we say the Spaniard who has a dog is in a house that exists on the street, right? So that's what we say here. Spaniard who owns the dog. Coffee is drunk in the greenhouse is coffee green. There is a house called Coffee in Green, and it exists in the street. And let's look at say cools are smoked in the house next to the house where horse is kept, right? So that's fact 12. So there is a house where cools are smoked, right, which is next to the house where the animal horse lives, right, in the street. So the thing that I mean, this is what is happening with all of the other facts, right? You can sort of go through it one by one in your own time. The thing that we are doing here is all of these are constants. Okay, these are all constants. We use the same street variable here. What essentially happens is there are lots of possibility for the values of the street, right? And by adding each one of these constraint, we are sort of constraining the shape of the street essentially. And the observation is that with all of these facts, there is a single street where you can know for each house what is the nationality, what is the pet that lives there, and so on. Okay, so when you execute this query, the street will be unified to something where all of the facts are obvious, right? And now the actual query, right? Who drinks water? Who owns the zebra? Is expressed this way. So I use the variable water drinker, right? I want to find out the nationality of the water drinker. So I'm placing this variable in the nationality position. The drink is water, right? I'm saying there exists a house in the street where water is drunk, and I'm going to use the variable for the nationality of water drinker, and similarly for the zebra owner, right, in the street. So once the street has been fully described, because of the constraint, it becomes fully ground. It becomes a ground term. There can be only one water drinker and one zebra owner, right? So that's the observation here. And if you execute this query, you get the result. So you get the configuration for, there are three variables, right? There is a street variable, there is a water drinker, and zebra owner. The street variable is unified to the actual configuration of the house. And we see that the water drinker is the Norwegian and zebra owner is the Japanese person. Okay, so that's the way you solve this query puzzle. What do I have here? So, any questions on this one? Yeah. Okay. So, if there are no questions, I'll continue. You can ask. Of course, you can ask questions later. So, the observation here is we added all these constraints, right? That constrain the house to a single result. So that constrain the street to a single result. There is only one possibility for the street. But if you give fewer constraints, then there are possibly multiple different street configurations, right? So this is what we see in this example. So the above query leads to exactly one street configuration. With fewer constraints, there are many more possibilities. So here I have a query where I say there exists a house with a British person, red house, right, in the street, and a Spaniard who owns the dog is also on the street. I'm not defining anything about the other houses, right, and I'm not defining anything about spatial positions of these houses, so they can be anywhere. So for this query, there are 20 different solutions, right? And 20 different solutions because there are 5 houses. There is one British red house, one Spanish house with a dog, right? And 3 other houses which are undefined. So you can work it out, right? So there are 20 different results. If you run this program, you get by default 10 results. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And the Jupyter notebook fetches the 10 results and just stops, right? If you wanted more than 10 results, we have a handy way to get more results. So we use the syntax with braces n, right? So we use curly brace n, and the idea is that for a query, if you use curly brace n at the end, it prints n results, right? If the number of results is less than n, it just prints up to those results and stops. If it is more than n, it prints n results and stops. I should say that this is specific to the Jupyter notebooks, right? As we saw earlier, the interpreter prints one result, waits for your input. You have to press semicolon to get it to print more results. But here you can just ask for, say, 40 results. We only have 20, but let me ask for 40. Prints the 20 results. Let me make it smaller. Oops. Yeah, it prints the 20 results and stops. You can work it out in your own time. So the key takeaway is if you wanted to see just one result, you can just give one here, or if you wanted more than one, you can do more. This will come in handy later. If Aman has a question. What is the 6th one? If I have in the query, it's 6. I don't know. I can't parse this question. Maybe you can ask the question, Aman.
So, like in the query,
Yeah.
exist only can have like the street can only have 5 houses, right?
Yeah.
But if in the query, if I give like, 6 exist queries, so like 6 house configurations, will it give error or will it unify?
It'll just say false. it says that it will return you and say, oh, I don't have a house which satisfies that. Let me try. I think it's, it should give false, right? This is the notebook is behaving differently. It essentially says, okay, I can't. It will say that I can't find the sixth house, so I can't satisfy your query. So the query is not satisfied. It is just like asking a query which is not true, right? So if it cannot satisfy, it just returns false. Yeah, I need to restart this thing. Anyway, so that's the idea. I want to show a different way of encoding this, right? The observation, if you sort of look at this, I encoded everything as part of the query itself, right? Both the problem and the actual query that I wanted to solve is all part of a single query here. So you can organize it differently. You can say the puzzle is defined over a street, and the puzzle has all of these constraints, right? It has one of these clauses, and you can now say with this puzzle street, which brings in all of the additional goals, right? It brings in all of the constraints. In which house, like who is the zebra owner, right? So there is a house where there's a zebra owner who owns a zebra. What is the value, satisfying value for the zebra owner in this street? And if you do this, you get that the zebra owner is Japanese, and similarly for the Norwegian. Yeah, this is just a different way of encoding it. Why did we not describe the initial queries as facts? So, good question, right? So we are not describing them as facts because we want to have the same variable to be used in all of these. We want the same variable to be unified across the different facts, right? If you describe one fact, if you describe another fact, right? If you use the same variable, I think they are implicitly different different facts. They are not unified together, because if you look at the way Prolog proceeds, right, it is not considering two facts together. It is considering one fact and then considering the second fact. The only way to take a variable and unify the variable across two different facts is to have it with this comma, right? A comma is disjunction, and we say that comma is conjunction. And what we are explicitly asking is this street variable is the same variable that is used across both of these goals, right? And that is what gives us the satisfaction, right? So that is what gives us the way to satisfy each of these street variables to be unified with the same thing. If you give it as separate facts, it won't work. You can try it out, right? And the intuition is that that's not the way Prolog works, right? SLD resolution looks at a single fact at a time. There is no way, if you give it as multiple facts, it will just look at them as individual facts. Okay, so moving on, I think that's the logic puzzle. I think we are right on time. Any other questions on this lecture? Okay, so if there are no other questions, what we'll do in the next class is we'll start looking at lists, and we'll dig a little bit deeper into how Prolog works with infinite programs, right? So, of course, Prolog has non-termination. What are the implications and so on? So we will start looking at it from Monday. Have a good weekend. Bye-bye.